These are the notes for AP Calculus on the topic of limits, graphical, analytical, both removable and non-removable, Hopital's rule, and disguised derivatives. So recall first of all the notation for limits. We have left-hand limits, where you have the limit of the function f of x as x approaches c from the left. And you can see that little negative indicates coming from the left side. And also the limit as x approaches, a right-hand limit is the limit of the function f of x as x approaches c from the right. Little plus sign indicates coming from the right. And then when you don't see the plus or the minus here, that's the overall or general limit, which means coming from both sides. The limit of the function f of x as x approaches c. So let's first take a look at determining these limits graphically. And let's start with the limit as x approaches -1 from the left. So from the left, here's where x is -1, and we're approaching -1 from the left. You can see the limit asks you, well, as the x value approaches -1 from the left, what is the function approaching? Or in other words, what is the y value approaching? We can see here that it's approaching 3 from the left. So your limit as x approaches 1 from the left would be 3. And then the limit as x approaches 1 from the right, I'll take our red ranger over here and head towards x is approaching -1 from the right. You can see that's y value is approaching -3. And remember, whether it reaches it or not doesn't affect the limit. It's just what it's approaching. So here it actually doesn't reach 3 there. Here it does reach -3, but either way, that doesn't affect the limits. And then for the general limit to exist, the left and right limits have to be the same. Since they're not the same here, we can say the general limit does not exist. Or we can abbreviate that capital D, capital N. Now let's take a look as x is approaching 0. So as x approaches 0 from the right, let's just not use the cars here for a minute. Okay, so as x approaches 0 from the right, sorry, from the left, here's where x is 0, so from the left, see it's approaching -2. From the right, x approaches 0 from the right, it's also approaching -2. So your general limit, in this case, those are the same, so your general limit is also -2. Now let's look at the limit as x approaches 1 from the left. Well, 1 from the left, you can see it's approaching -3. And as x approaches 1 from the right, also approaching -3. So your general limit would also be -3. Notice this point down here has no effect on the limits whatsoever. It affects whether it's continuous because it's not continuous at 1 because of the hole, but it does not affect the limits because it's not approaching -5 from either side. Then as x approaches 2 from the left, at 2 we've got a vertical asymptote. So 2 from the left, you can see the function's heading down towards -infinity. As x approaches 2 from the right, the function's going to infinity. And since those are not the same, the general limit we can say does not exist. Now let's look at as x approaches 3 from the left, it's approaching a y value of 3. From the right, the function is approaching a y value of 3. So your general limit is 3. Then as x approaches 5 from the left, it's approaching 1. 5 from the right, also this one's approaching -2. So your general limit as x approaches 5 does not exist. Those are not the same. then the limit as x approaches negative infinity. Well, for negative infinity, we're going to look as x goes to negative infinity, the far left part of the graph, which is right here. And see that keeps going up forever, so the y value goes to infinity. And then as x approaches positive infinity, we look at the far right of the graph as the x heads to infinity, but this time it doesn't actually go to negative infinity. It doesn't go down further because there's a horizontal asymptote at y equals negative 4. So it's getting closer and closer to negative 4. Now let's take a look at when you don't have the graph. Evaluating the limits analytically with the equations. And we've got two main types we're going to look at. Removable discontinuities, those are holes. And non-removable discontinuities, those are vertical asymptotes. So when you have a hole, there's two ways of handling it. You can, when it indicates you have a hole, you plug in using direct substitution what x is approaching, t value, and you get 0 over 0, which is indeterminate. Then you know you have a hole at x equals c, and the limit actually does exist when you have a hole. The general limit's going to exist because it's going to be approaching the same thing from the left to the right. And some of the methods you can use are factoring, rationalizing, simplifying to remove the hole and evaluate the limit. Or, remember, you can also use the Hopital. So this is saying if you get this determinate form of 0 over 0, when you're evaluating a finite limit, then you can basically take the derivative of the numerator and denominator separately and plug in what x is approaching, and that'll give you the correct limit. Then we also have non-removable discontinuities, which are vertical asymptotes, and that's when you get something undefined, like 5 over 0 or negative 2 over 0, where that numerator is anything but 0. There's the vertical asymptote, and then we have to employ the left and right hand test to see if it's positive. We'll go over in just a little bit. All right, so the first thing you do when you're evaluating these limits is you substitute in what x is approaching. Negative. So we'd have negative 3 squared minus 9 divided by negative 3 squared plus 3 . Well, that gives you 9 minus 9 is 0 over 9 minus 9 is 0. So that what that tells you, remember, is you have a hole at x equals negative 3. That means in order to get rid of that hole, we need to cancel what's causing the hole as an x plus 3. So we can use, let's show you how to do this one in two different ways. You can use factoring. Take the numerator to x minus 3, x plus 3. Denominator, you could take out the x, leaves you with x plus 3. And then you can remove the hole. These are called removable discontinuities. And as soon as you do that, then you can plug negative 3 back in. So what's left? Negative 3 minus 3 over, there's an x there, so negative 3 gives you negative 6 divided by negative 3 is 2. Now the other way to do this is using the Hopital's rule, is only for when you get the indeterminate form of 0 over 0. Remember what that says is you take the derivative not of this whole thing using the closure rule, but treat the numerator and denominator as two separate functions. So the derivative of the numerator is 2x. The derivative of the denominator is 2x plus 3. And then plug in what x is approaching, negative 3. So you get 2 times negative 3, or 2 times negative 3 plus 3 gives you negative 6 over, that's negative 6 plus 3, negative 3 equals 2. Now let's take a look at the next one here. On the next one, we substitute again what x is approaching, in this case 0, so we have 3 times 0 squared over the cosine of 0 minus 1. So that gives you 0 on the numerator. Cosine of 0 is 1 minus 1, so you do get 0 over 0. Which again indicates there's a hole at x equals 0, and that means we need to cancel x. However, well, you can see an x on the numerator because the trig function can't just take the x out of the cosine. So again, we got 0 over 0, so this one we definitely have to use the Hopital's rule, unlike the other one where we had a choice. You could do it either way. Okay, so remember you take the derivative of the numerator and the number separately, so 6x over derivative cosine of negative sign, x, or negative 1 is 0. And then plug in 0. So you get 6 times 0 over negative sign. But that's still 0 over 0, so that didn't seem to work very well. Well, with the Hopital's rule, sometimes you have to use it more than once. So eventually we'll get something that's not 0 over 0. So let's take the derivative of these separately again. Derivative of 6x is 6. The derivative of sine is cosine. Now we get 6, and now when we plug in 0, cosine of 0 is 1. So it's 6 over negative, and then cosine of 0 is 1, so we get negative 6. On the next one, we substitute in 2 with x to the function. We get 2 minus 3 divided by 2 squared minus 4 times 2 plus 4. So that gives you negative 1 over, that's 4 minus 8 plus 4 is 0. So when you get undefined, something that's not 0 divided by 0, that's undefined. That indicates you have a vertical asymptote. In this case, at x equals 2. Let's draw that a little better here. And so then what we have to figure out is what's happening on the left and on the right. So the limit as x approaches 2 from the left, I'll just call this f of x. Well, remember you use the sign for the numerator, which is a negative, so negative divided by. If you plug in something to the left of 2, like 1, that'll be 1 squared, and it's 4 times 1 is 4. Gives you a negative divided by 4's cancel here, positive 1, so that's negative. So now we can see from the left, approaching negative infinity. And let's try the limit. X approaches 2 from the right. Again, we have the negative on the numerator. From the negative 1 we go right there. Over from the right is 2, like 3. 3 squared minus 4 times 3 is 4. So you get negative divided by 9 minus, sorry that's hard to read there, that's negative 4 times 3, so negative 12 plus 4, that's 13, 9 plus 4 minus 12, that's positive 1. So from the right it's also approaching negative infinity. Look at that. So that tells us, since those are the same, the overall limit as x approaches 2 of this function, I'll call it f(x), equals negative infinity. If these had been different, if one had been positive infinity, one had been negative infinity, then a general limit would not exist. Now let's take a look at one that's a little different. So if we start on this one, that considering we must have an integral in there. Integral from 0 to 0, e to the t minus 1 dt over 0 cubed minus 3 times, cosine of 3 times 0 is just 0 plus 1. With the integral from 0 to 0, there's no area enclosed there. That's just going to be 0. And that's 0. The cosine is 1. Cosine of 0 is 1. That's negative 1 plus 1 is 0. So we get 0 over 0. So we can use the Hopital's rule. Because this one is not one you can simplify easily on the numerator without it. So the Hopital's rule again says you take the derivative of the numerator and denominator separately. So we take the derivative of the numerator, which looks like this. And the derivative of the denominator would be 3x squared. Drift cosine is negative sign, so the negatives cancel, plus sine 3x times 3, and the derivative negative 1, 0. So, remember this is now the second fundamental theorem of calculus when you have the derivative of an integral. As long as this is a constant, which it is, it's 0 in this case, then all that happens, the derivative integrals are reverse operations. So remember they cancel out if this is a constant, and the x this variable just replaces this one. So that's going to be e to the x minus 1. And when you plug in 0 into that, you get e to the 0 minus 1. That's 1 minus 1 equals 0. And so then when you plug in 0 in the denominator, you get 3 times 0 squared plus the sine of 0 minus 3. So you also get on the denominator 0 plus sine of 0 minus cosine of 3. Let's see, so this is actually, there's no minus 3 here, sorry about that. This is a times 3. So 0 times 3, so that's 0 plus 0 is 0. So you do get 0 over 0 again, so you have to use L'Hopital's rule one more time. Now we take the derivative of the numerator, derivative of e to the x is e to the x. Derivative of negative 1 is 0. Derivative of 3x squared is 6x. Derivative of 3 sine of 3x would be positive 9 cosine of sine x. Cosine of 3x, sorry. Because it's already been multiplied by 3, we can take the derivative of sine times the 3 that's already there gives you 9. And then when you substitute in 0, you get e to the 0 over 6 times 0 plus 9 times cosine of 0. So you get e to the first 1 over 0. Cosine of 0 is 1, so that's 1 over 9. Take a look at another one, it's a little bit different. Again, in this case, 3. Go from 3 to 3. T dt over 3 squared minus q. So that's just going to be 0 over, because again, go from any number to itself is just 0. And you get 3 squared of 9 minus g of 3, is 9. So you do get 0 over 0. So we can use the Hopital's rule. And then again, when you take the derivative of the integral from 3 to x, it's just going to get you g of x. If this variable just replaces this one, it's the second fundamental theorem. And then the derivative of the denominator is 2x minus the derivative of g of x is g of x. So now when you substitute in 0 again, g of 0, or you substitute in 3 again, g of 3 is 9 over 2 times 9 minus g prime of 3 is also there, which is 5. So we get 9 over 18 minus 5 is 13. I also got a different type of limit, which are disguised derivatives. And these don't look the same as other limits because you have h approaching 0, and h is really just another way of saying the change in x. You can see this really just comes from the slope formula. The difference of the y's divided by the difference of the x's. So h in this case is really the same as delta x. And so when you see a limit like this, you just have to recognize, oh, this is not an ordinary limit. This is the definition of the derivative. So this equals the derivative of some function. And then the way you figure that out is figure out what the function is. You can see right here is f of x. So in this case, f of x is cosine of x to the 4th. And when we take the derivative of that, f prime of x, using the chain rule, would be 4 cosine of x cubed times the derivative of cosine is negative sign. And that's it, because this whole limit is equal to the derivative. You could simplify it a little bit. You could simplify it to pull the negative out front, so it would be negative 4 cosine of x cubed. So, all right, let's take a look at one more of these. Again, you can see this is h approaching 0, not your typical limit. And you can see in this case, f of x is right here, e to the 2x. So f of x equals e to the 2x. And again, this whole thing equals the derivative of some function. We just found that function. So the derivative of f prime of x using the chain rule will be 2 e to the 2x. Okay, let's go one more. Again, it's a definition of derivative. It's a little different here. So it's equal to the derivative of some function. But notice there's an a there instead of x, so this represents f prime of a. And they tell you it equals 1/10. Based on that, we'll figure out what. So let's figure out what the function would be first. Right here, except it would have had x first before it. So f of x would be arctangent of x. Then when you take the derivative of arctangent, that's 1 over 1 plus x squared. But in this case, we've got a there. So f prime of a will be 1 over 1 plus a squared equals 1/10. Then you can cross multiply. 1 plus a squared times 1 is 1 plus a squared. 10 times 1 is 10. Then subtract the 1 over. Squared equals 9. A equals 3. And that concludes the notes for AP Calculus on the topic of graphical analytical limits. Graphical, analytical, both removable and non-removable, Hopital's rule, and disguised derivatives.